I'm going to now look at some trends in the periodic chart. We'll start off with electronegativity, which is a relative measure of the strength with which an atom pulls electrons towards its nucleus. And what we're going to find is that this is related to both ionization energy and to atomic radius. But we'll start off with the electronegativity, and the most being fluorine. The electronegativity is measured on the Pauling scale, which goes from 0 to 4, with fluorine having the highest value, which is 4. You'll notice that the noble gases don't tend to have very high electronegativities, and the reason for that is because they don't really need electrons. They've already got full outer shells, so that means that their electronegativity is not very appreciable. Fluorine, on the other hand, has 7 electrons in its outer shell, would like to have an extra electron, would really like to have an extra electron, so that contributes to making it the most electronegative of all the elements. The least electronegative would be francium, and what we notice is that electronegativity will tend to decrease going increase going up the columns, and increase going from left to right across the rows as well. So really all you would need to know is that fluorine is the most electronegative element, while francium would be the least. If we take a look at ionization energy, that's going to be the energy required to remove the outermost electron from an element. And what we're looking at here is helium being the highest ionization energy. That's the one that's hardest to remove an electron from. And there's 2 reasons for that. First of all, the electron we're removing is part of a full outer shell, so helium doesn't really want to give that up. And the other thing is that that electron is going to be very close into the nucleus because of where it is on the periodic chart. The closer electrons are to the nucleus, the harder they are to remove, and the more energy it takes to remove them. Francium, on the other hand, would have the lowest of all the ionization energies. Now, just to put this into a little bit of context, if we take a look at something like sodium and potassium, you can see that potassium has entirely new or one more extra row of electrons that sodium does not have. That means that the outermost electron in potassium, for example, is further out from the nucleus than the outermost electron in sodium. And this will mean that sodium will have a higher ionization energy than potassium will. So we see ionization energies will increase going up columns, and will actually also increase as we go across the rows as well. And this is going to be related to atomic radius. And atomic radius will decrease going up the columns, and the reason for that is because with each additional row we're adding a row of electrons. So this it's like sodium and potassium. Potassium will be larger than sodium will be because of the extra row of electrons. But what's kind of surprising is that atomic radius actually decreases going from left to right across the periodic chart. You might expect that if we're adding protons here and adding electrons, that we would end up increasing the radius, but that's not what happens. What we see is that lithium, for example, actually has a larger atomic radius than fluorine does. Now, the reason for that has to do with the electronegativity, or is related to that. If you've got lithium, what you've got here is 2 electrons. You've got 2 electrons in the center, and you've got this 1 electron on the outside. And we've got a nucleus here, so that's for lithium. But we're going to keep on adding electrons to this, and we could do the next one, which is beryllium. And what's going to happen is that we're going to add, this is going to be a 3+ charge. We add another charge to the center. But what's key here is that we're not adding another row of electrons, we're just adding another electron to the same row. And what happens is that these electrons will actually get pulled in closer because we keep on increasing the proton charge in the center without increasing the number of electron rows. Just the number of electrons is what's increasing. So when we get all the way over here to fluorine, what happens is we've got the 2 electrons in the center, we've now got 9 protons, and we've got 7 electrons on the outside. And those 7 electrons are now going to be pulled even closer in towards the nucleus. And the reason for that is because we've now got a 9 plus charge in here as opposed to a 3 plus charge. And while we've been adding electrons, we haven't been adding any electron rows. So what happens is the atomic radius will actually decrease going across the row from left to right. This also has an effect on the ionization energy as well. So the ionization energy will be smaller for lithium because this outermost electron will be further out from the nucleus than it would be for, say, fluorine, which will have the electrons closer, the outermost electrons closer in to the nucleus. The other thing with fluorine, of course, is that it doesn't want to give away electrons, it wants to gain them. So taking electrons away from fluorine is going to be much more difficult than something like lithium as well.